Our first presentation will be by Dr. Anoosh Shamsabadi, a senior bridge engineer with 31 years experience in CALTRANS in the USA. He's in the California office for earthquakes, and I'm sure what he will show you in terms of solid structure interaction will be enlightening to all of you. Okay. The title of the talk is Structural and Geo-Engineers Handshake, Seismic Design, Tunnels and Bridges.
Thank you very much for the nice introduction. So, any presentation I go, I've got to put this disclaimer because I work for government and I cannot represent government, so I just put a disclaimer that I work for California Department of Transportation, Office of Earthquake Engineering, but on my own and I'm on vacation. That's what I have to say because I work for government. So, anyways, we will be discussing a few things, including principle of seismic design. We will discuss seismic loads, geo and structural engineers handshake, how they work together. We will discuss calibration and implementation of some of this global model in Diana. And at the end, I will wrap up my presentation using the latest and greatest of build for liquefaction, lateral spreading. This is a big concern now for seismic design of bridges. So, the basic philosophy for bridge design, or any design, is simplicity. You need to design the structure as simple as you can, so you can understand the clear load path. Symmetry. You want to design the structure as symmetric as possible, because for seismic, if you have unsymmetrical structure, you get all kinds of crazy behavior like torsions and so forth. And of course, integrity of the structure, adequate connectivity, like you try to avoid as much as possible, not having joints, gaps in the structure, because for seismic, it is not a good idea to have these type of features in the structure. However, sometimes you cannot avoid complexity of the structure. It's like you have a structure like this, which is dictated by the fluidity or by the roadway design, and you have to design a structure like this. It's very complex. As an engineer, you have to deal with it and design a complex structure. Another complex structure, is dictated by the traffic, and these structures are very complex, and therefore, as an engineer, you should sharpen your pencil and design the best structure that you can. And for this type of structures, therefore, you need to have a proper tool. With this, I'm going to start with the demand of a structure and seismic loads. Basically, you design the structure either using the spot spectral approach or the displacement approach. Nowadays, with the design tools that we have, we are trying to get away from the spot spectrum and basically use a displacement times history approach. The only word of caution is how do you come up with these motions. That's really the challenge, which is the demand side. These days, to be honest with you, I think with all this computer technology and with these software that we have, it is not hard to capture the capacity. It's on the demand side, and the demand side comes from the seismic. So that's the challenge, to come up with a proper loading. Okay. Before this conference or the seminar, we had a lot of discussion what should be the title, and then looking at the Diana capability, we thought we should really call it the handshake between structure and geotechnical engineers. And not only geotechnical engineers, but what the geo-engineers. And see how they should work together to come up with a good product. So that's what I call this a seismic SFSI, which is seismic soil foundation and structural interaction. The team members are geo-engineers, which include engineering geologists, not the geologists. It should be engineering geologists because it should be an engineering geologist that understand what the engineers need for the design. Engineering seismologists, another way you cannot just have any geophysicists to develop the ground motion or the earthquakes. It has to be an engineering seismologist that have enough understanding of engineering approach so we can communicate with engineers when they request a ground motion. Of course, geotechnical engineers, and again, geotechnical engineers, you can't really work with the classical so-called geotechnical engineers. It's not about doing consolidation tests and so forth. This is about doing seismic and basically having enough understanding of the structure. So when the structural engineers request foundation springs and so forth, they will understand what needs to be done. And of course, at the end, everything lands on the design and analysis team, which is the structural engineers. And the structural engineer is the person who stamps the plans, and he's responsible for the final product. Anything goes wrong, he's not going to go back to the geotechnical engineer, engineer, seismologist, or geologist. You stamp the plan. I mean, you should have asked the right question. That's why you should have a handshake. You should basically, structural engineer should have enough understanding of each one of these disciplines so he can make sure that he gets the right product. So this is one of the structures that I was involved with the retrofit. It's a Vincent Thomas Bridge in California, Long Beach. And this is an example of how we work with geotechnical, geoprofession, and structural engineers. So first, we did all the drilling, and we had a group of geologists. Engineering geologists, they did the fault rupture study, and they came up with the fault rupture data. Then the seismologists came in, and they developed attenuation relationship, probabilistic seismic hazard study. Some of these terms, if they're not,
no, it's just as it.
Oh, I can speak louder, by the way. Yeah. If you hear me okay, if not, I know. It doesn't matter. Maybe I don't think I need this. It's up to you. You want me to use it or? Yeah. I can speak louder. So now we have the engineering seismologists. That, like I said, they use attenuation relationship to come up with the proper seismic wave, seismic displacement time series, and also they need to do probabilistic seismic hazard study to make sure that you do all the probabilistic, because everything we do these days, as far as developing ground motion, is based on probabilistic seismic hazard study. Now, if you don't understand these terms or you haven't seen them before, it's okay. In the future, there is a plan that we will set up a workshop using through the Tina Diana, and basically go through all these different workshops with example problems, how do we develop these, and how we apply them to the global bridge models. Then comes the geotechnical engineers. The geotechnical engineers, they will do the site response. They get the rock motion from seismologists. They propagate the rock motion through the surface or at the level of the foundation to the structural engineers. And all these three, they work together. In other words, first engineering geology comes into place. If they did that to seismologists or engineering seismologists, it goes to geotechnical engineers, and finally structural engineers has to communicate with everyone through all this process. You cannot stay at the end and say, give me the ground motion. You have to be involved as a structural engineer or whoever is stamping the plan. You have to be involved with this from day one. And that's what we call a handshake. Now, these guys from my course that we see, as a matter of fact, they're from USGS. When we were doing the retrofit for this particular structure, we were supposed to do seismic instrumentation in the ground all the way to 600 feet in the ground at various depths. 600, 350, and on the surface to look at the ground motion during seismic event. They were studying actually floor rupture. When I was looking at this, I said, I thought this was just looking at the dirt. I mean, they pull a sample, they're looking at it. But actually, they're measuring, this is the greatest slide, actually, one of the best I've seen. They're actually looking at floor rupture. You see, this is the one piece, and then all this intact piece, and then they were excited about this particular sample. And they said, oh, we think we find something that is very disturbing. And they were basically looking for fault. Now, there's a lot of background with this slide here. I cannot show everything because I have only half an hour. But as an example, what structural engineer and seismologists understand is basically development, they're developing the ground motion. If you look at this motion, this is from a subduction zone type of motion, like chili type of motion. So I'm involved with the project right now. I'm not going to name the project because it's in development. And this project is located in the subduction zone. So as a structural engineer, I need to understand when I request the ground motion from the engineering seismologist, I need to understand this ground motion with the subduction zone. Their amplitude is not too high and they have a long duration. So therefore, my structure is going to be excited for many cycles. Even though the amplitude of the motion may not be that high, for example, in this case, I have only like 4 or 5 inches of deformation maximum. But the duration is 120 seconds. So my structure is going to go through many cycles. Something may happen to me because of all the cycles that it's going to go through. Or if I'm in a zone that is a strike-slip fault, the amplitude of the motion is very high, but the duration of the motion is low. So that's another thing that a structural engineer should understand, where the structure is located. If it's located in the area with the subduction zone, duration of the motion is long. So therefore, you need to basically design a structure that handles the long duration. So again, what happened? Engineering seismologists create the motion at the rock level after talking to the geologist. Then geotechnical engineers propagate the motion using side response. And that's what you can really do with the classical geotechnical engineers to understand dynamics. Here we're not talking about just C and P. We're talking about basically stiffness in the screw. They deal with G over G max and all that stuff, which is the stiffness. And then structural engineers develop the model, shape the structure, and at various locations of the structure, basically we come up with a response of the structure, either displacement time history of the structure, shear versus moment, or shear versus time, displacement versus time, and design the structure for that kind of response. Now, what I'm talking to you is all from experience actually. These are all the structures that we've been dealing with. If you get a fault, for example, this is from one particular structure that we're working on right now. So if I have a fault, this fault is going to have different segments. This is on one particular structure actually. And it's a three-dimensional problem. Basically, you develop three-component motion. So we have a fault normal motion in the normal direction. Then you have fault parallel. And then you have the vertical motion. This is what seismologist is going to generate at the rock level. My structure is located here. And it's not a straight structure, it's a curved structure. Not only is the geometry is curved, but it's got all kinds of nonlinearity, joints, and so forth. How am I going to apply the motion here? So when you talk to the seismologist, he's going to give you a motion at the rock level and say, hey, what about orientation of my structure? What am I going to do with this? That's why geotechnical engineers, seismologists, they need to get together how to resolve this issue and how the motion is going to get transferred to this structure. Another structure. How am I going to apply the ground motion? Seismologists gave me ground motion at the rock level. Geotechnical engineers did a site response, brought the motion to the surface or at a given elevation. How am I going to apply here now? I need to apply, and every support is going to take its own motion. How am I going to apply this to the structure? So again, when we were talking about, we didn't have the codes. Code says, design the structure as simple as you can. All this stuff that we talk about, when you come to reality, that's not the case. I mean, I'm given the structure to do the design. It's not simple by any means. Okay, so that's where we talk about structural engineers, technical engineers, engineering seismologists, that they have to resolve this ground motion issue. I have another structure. Actually, we have developed a full 3D model from the structural engineering of Diana, both beam spring models and continuum models, which I'll show later on. This bridge is instrumented. We have instrumentation all over in Northern California. And if I apply the ground motion to this bridge, it's simple. Because it's a straight bridge, I can apply vertical motion, transverse and longitudinal motion, no problem. What about this bridge? So this bridge actually, if I orient this to my global orientation, this bridge is turning. All of a sudden, my fall normal, they become fall parallel at this bridge. So it's very complex, and that's why all these disciplines, they should work together. Geotechnical engineers and engineering seismologists, they need to work together to see what they need to deliver to the structural engineers, and the structural engineers need to understand what they do. Did they orient the motion correctly when they gave it to him or not? Again, I'm talking about experience. We went through a lot of problems with not having the correct orientation of motion. We do the analysis, come back, nothing makes sense. Well, what happened? Ground motion is not good. Why ground motion is not good? Engineering seismologist, I give you the correct motion. Geotech, I did a site response, and then what like to make sense? Orientation of the motion. Not only that, but there are a lot of other things that we need to do for the motion, called cross correlation and so forth, which we don't have to discuss now. But that's the biggest issue. I don't care what kind of a computer model you develop, no matter how good of a model, detailed model you have. If your ground motion is not good, it doesn't matter. Basically, everything is wasted. And that's what demands it. Now, this is a very simple response spectrum. Again, if you talk to the geotechnical engineers, they always give you a response spectrum. Very simple, single degree frequency. So that's what you want to get. As a structural engineer, my recommendation, or even as a geotech, you need to look at not the real response spectrum, you need to look at the displacement spectrum. And many times, when you get it, you're given a response spectrum from a geotechnical engineer. If you take the displacement response spectrum out of it, it doesn't make sense. So you have to look at both of them. So this is the response spectrum, acceleration versus period. This axis shows you displacement versus period. It's very simple to calculate. All you do, displacement is equal to 1 over 4 pi squared, at squared. You have all the a's. All you do is square by period, and you calculate your displacement and plot the displacement. And I'll show you what could be the problem if you don't do this. So, again, go back to the basic design philosophy. Conventionally, we always design structure at capacity is larger than demand. That makes sense. You design a beam, it has a load on it. You want to make sure that you design the beam, the load is less than the beam capacity. Now, we're working on new alternatives, which basically you want to make sure your demand is less than capacity. Now, I said, well, that doesn't make sense. You're telling me capacity less than demand, and you're just reversing it here. I'll get to this later and see how to do this now. Instead of fighting the demand and making the capacity bigger and bigger, work with the demand, be friendly with the demand, and say, hey, let's work together and make the structure flexible so your demand and your capacity, they work together. Don't fight it. So, to do this type of things that we talk about capacity and demand, basically this is from Ashton. This we when we design a structure, we look at two alternatives. You want to make sure that your substructure is ductile and your superstructure is elastic. Another way, you want to make sure that your columns move nicely during the earthquakes. Nothing happens to the column, but superstructure should really stay elastic. So your columns are flexible, ductile. You can form plastic hinges in the column, but nothing should happen to the superstructure. So that's what we call ductile substructure and elastic superstructure. By the way, when we talk about in bridges substructure, superstructure, which is the deck of the bridge, is your superstructure. Anything below deck, including column, is substructure. It's not just the foundation. So we want to make sure conventional design for seismic, you have a ductile substructure, elastic superstructure, or you do ductile. You want to have ductile superstructure and maybe elastic substructure. Personally, I don't like this. You don't want that much, but I'll tell you what it is. Or why not design superstructure and substructure elastic? Now, I hope you understand what I'm talking about when I said superstructure and substructure both elastic means we don't want anything happen to them. We wanted to make sure that they go through earthquake, they stay elastic, they move, they come back to place, to the original location without forming any plastic hinges or doing any repair to it. That's the ultimate goal. That's the alternative. That's actually what we're fighting to do now. And I want to just, as far as geotech, what geotech is going to do with this? So you need to understand when the structural engineer says this is what I want to do. As a geotech, you need to see what is it that you need to do and what kind of recommendation foundation design you're going to make. So this is the conventional seismic design. We want to have ductile substructure and elastic superstructure. Another way, we want to force all the plastic hinges in the column. And I force plastic hinges in the foundation. You don't want to do this. You don't want to do this because you want to make sure your foundation survives. That's what we call capacity protected foundation system. You want to make sure nothing happens to your foundation. Foundation are the most expensive part of the bridge system, and if something happens to them, you're dead. You cannot repair. And you cannot inspect it. So that's why we want to make sure that our columns are ductile. We force the plastic hinges in the column because we can always go repair the column. And remember, the ultimate goal is to keep the structure alive. You don't want it to happen to the superstructure. You want to let it come down. So, again, when we talk about ductile system, I have just one simple example problem. I have a response spectrum. And basically, we want to make sure that during the seismic event, the bridge goes left and right. The column should stay ductile. How do we calculate the period of the structure? 2pi m squared K1, that's very basic. I have the mass of the structure, I have the stiffness of the column, and even I can include the stiffness of the abutment, and just use this equation, I can calculate the period of the structure. Very easy. Then I know the period of the structure, I can go to the response spectrum and read the force. That's why I do elastic design. Now if I make the structure ductile, that means these columns, they can move back and forth. It becomes a soft system. That means I'm increasing the period of the structure. So period from T1 equals to T2, and I go to the response spectrum. Instead of putting a force S1 in the structure, I'm putting a force S2 in the structure. That means it's going to take less force. But that means it's going to take bigger displacement. Because it's more flexible, make the structure flexible, it's going to take less force, but bigger displacement will do it. I'll show you later on. So, when we talk, this is the conventional seismic design we were doing. In elastic design, soften the stiffness and elongate the period of the structure. But we design for it, so there should be no problem. And that's why we should always look at the displacement spectrum, not the acceleration response spectrum. Because you look at the acceleration and say, oh great, I reduced my forces. What happened to the displacement? So there it is. I have one structure with a T1. I can read my acceleration from this end, and I can read my displacement from this other end. That's why you want to have both. Now, remember when I said principle of seismic design, you want to make sure that your structure is balanced. Balance, mass, and stiffness. Well, let's look at the structure here. This is actually one of the projects that I worked on. The source properties are almost the same. The source profile is a real project. So I have rock here, very confident rock. And then I have some soft soil. I have the hard foundation and so forth going into the ground. So, do you think there is anything wrong with the structure here? I have very large diameter shaft extending all the way to the rock, but these two, they don't have to go to the rock. But that's really not a good design. And the reason for that, because these columns are short, and when they're short, they absorb a lot of load during the seismic. So therefore, we need to isolate these columns. And that's what we do. You drill a hole in the ground, and this diameter of this hole should be larger than the diameter of the shaft, so that you can balance the stiffness between the columns. So everything moves together during the seismic event. Otherwise, you're going to break something. If the columns are too short, they're going to absorb more load, they're more stiff, and you're going to break them. This is an example of isolation. Basically, we had this bridge. The other columns were too long, and then we had to do column extension and develop this corrugated pipe in the ground with isolation, so it would be flexible on the other columns. Now, so that was a type 1 structure. Type 2 structure basically is only for steel bridges. And instead of making the substructure flexible, they said, why don't we have the superstructure ductile and flexible? For a steel structure, then recommendation is make these cross frames on the steel structures at the pipe and the cap, make them ductile, make them basically that they take ductility, but to be honest with you, I wouldn't do that. I mean, it works, but that's not my. I wouldn't do this. I would basically either have a type 1, which is ductile substructure, or ductile elastic sub and superstructure. Now, type 3, that's my favorite, and that's my preference as an engineer. Somebody may not like this. And nowadays, we are actually trying to go to this approach. That's the actual recommendation. And we have type 3, and we're using elastic superstructure, elastic substructure. Remember, I didn't put any plastic hinges in the column because I don't want the column to form any hinges. I want to make sure during the earthquake they move back and forth and they come back to the original position. But we use isolation bearing. With the isolation, we can isolate the superstructure and substructure by inserting isolation bearings. It works great for earthquake, and your structure survives. So in this case, remember I showed one slide which I was basically extending a corrugated pipe all the way to isolate the columns so they move together. But in this case, all I have to do, instead of using corrugated pipe and doing the isolation casing, I just put the isolation bearing at top of the columns. And the bottom, everything is isolated. And so the superstructure and the substructure, they're isolated. Superstructure is not fighting the earthquake, basically it's dancing with the earthquake, and all the energy is absorbed by these isolation bearings. And this is an example of isolation bearing in one of the bridges. That's actually close to the neighborhood where I live. I don't know if we can dim the lights so we can see the isolation here. I don't know if we can dim it here, but there is nice isolation at top of these columns. When you look at this bridge, you're thinking that, oh, it's an arch bridge. Actually, it is not. These arches are just aesthetic. They don't do anything. They're from light and concrete. The superstructure is supported on column, and columns are separated by isolation layers. I'm involved in a bridge right now. The new design of the bridge, actually, I'm doing the analysis for this bridge. And we are putting the bridge on isolation layers. So, to isolation. A couple days before I make a trip here, I went to the isolation yard. Actually, I work with them very closely. And this isolation, they vary in size. You could have small size, you could have large size. It depends on the size of the structure. This particular one, I was told, is for a offshore oil platform, and it's about, I believe, almost over I think almost 3.5 meters in diameter. So it's supporting isolation, it's supporting the oil platform. And they do all kind of testing there, make sure that, you know, what, I'm sorry? What? Oh, I'll show you. I'll show you what they are. So there are different kinds of isolation. This one is called triple pendulum isolation. Again, because we don't have time to go through all of them, I just show you what they are. But hopefully, in the near future, we will show you the sample calculation of how you design it. And if you have time, I can actually, after the break, I can actually have another presentation to show you how you design these things. Because I do it. So this is another form. There are some kind of, so they have, they come in different shapes, and as far as material, there's some kind of special Teflon that goes on these houses. So, yeah. Now, this is one bridge that I was involved, also doing a retrofit. So, I showed you two bridges with a, for a new design. One of them I'm already working on it actually, but this is retrofit one. So, we wanted to retrofit this bridge, and the pile caps are very large. This is actually the shipping channel. We could have gone with the conventional seismic design, which we have to enlarge the columns and retrofit the foundation. To retrofit the foundation, we have to build coffer for every single foundation here and go ahead and add large diameter piles. It would be very, very expensive. Probably more expensive to do the retrofit than replacing the bridge. So we decided we go with the new concept, isolate the bridge. So we put isolation on the top, and during the earthquake, because earthquake is all based on probability, there is a probability that the earthquake may exceed the capacity of the isolation. So isolation is moving, all of a sudden isolation may fail. That means you're going to have friction coming from the superstructure to the column, and the load is going to be transferred to the column. In order to avoid that, all we had to do was just put braces between the two columns. Make the column a little bit more stiff and original configuration. And we didn't have to do anything with the foundation. This is how this is for retrofit. Typically, these isolation layers are not too tall, because we have to jack the structure. We have to jack it up and slide this isolation underneath. Like this. This is actually going to be a lot of that. What's up? What's here on? I was going to show calculations this case. Okay, so here is how this isolation works. Not only they isolate the superstructure from substructure, but they give a lot of damping because it does all of this thermal damping, so it reduces the force and the displacement. Elongates the period of the structure, but because it increases the damping, it reduces also the displacement to some extent. This is an example of one of the isolation on a computer model. So we can see how this superstructure is isolated from the substructure, and this superstructure is moving around. As long as the isolation is large enough to take the displacement, no problem. So, if you're looking at a response spectrum, this is a response spectrum zeta 1 with a damping, let's say 5%. If you increase the damping, response spectrum actually becomes smaller. And we look at the displacement. So here is the displacement of the response spectrum with, let's say, 5% damping. This would be, let's say, 10% damping. So you can see the displacement also reduces. So if I have a structure with a 5% damping and a structure with, this would be my displacement, force, displacement, and if I start increasing the damping, my force comes down and also the displacement comes down. And this is what isolation bearing does for you actually. It would, because of the increase in damping, it will reduce the displacement. So, this is directly from Ashton. I just modified the figure, make it more friendly. But what happens with isolation, if you have a response spectrum, period 1, this is your force, and this is your displacement if you have no isolation. If you put it on isolation, the period of the structure increases. If the period of the structure increases, that means you want to get a bigger displacement. Your displacement will be way up there. However, because of the damping in the isolation, the damping reduces the force and the displacement, and instead of getting this displacement, it reduces your displacement as well. This is the advantage of isolating the structure. It increases the damping, that means it reduces the displacement, and also definitely reduces the force big time. Now, well, geotechnical engineer, structure engineer, isolation, what do you do? Well, there's always this notion that for soft soil you should not be using isolation there. And the reason because the pit in the soft soil period is already too long when you have a soft soil. And the period is already too long, and you put isolation on top of the site that has a long period, not only is not going to help you, but it could hurt you because your period is already too long. You want to make it longer, it's not going to help you. However, we still put isolation on soft soil because it is really not the free field that is shaking the structure. It's the motion that filters through the piles, goes through the column before it gets to the isolation. So it's really some type of a kinematic motion. It's not the free field motion that is shaking the structure. That's my own understanding because people, when they talk about isolation soft soil, basically they're talking about buildings sitting on soft soil. For reasons that kind. So again, you can see how isolation is going to help you to reduce the motion because it's really the kinematic motion, not the free field motion that is the structure. So I'm pressed with time, I guess. So if you have a soft soil and structure is telling you he wants to isolate the structure as a geotechnical engineer, you need to make sure you design foundations that are stiff. Do not design soft foundation. Do not design small diameter pile because they're flexible. They move with the ground. You don't want to do this. So if a structural engineer is telling you, I want to put the regional isolation as a geotechnical engineer, you're the one making a final recommendation for the foundation. You need to design stiff foundation. So the motion already gets reduced before it goes to the structure. And that's, again, that's why you really will need to work close with the structure. So, or in already involved designing, we actually put in the structure of ladder pile. Because ladder pile, they can reduce the motion if it's in the soft soil. This is one of the project in the Bay Area, Barry pile. This gentleman is a lot taller than I am, and he couldn't reach the top. Very large diameter piles. So this is the type of foundation we want to recommend as a geotechnical engineer. Make sure that you do some kind of column extension or vertical when the structure goes on isolation bearing, so the motion gets in. This is another type of shaft, but I'm not going to let you discuss it because the screen is already looking at me. So this is one project I'm working on right now. It's going to go on isolation bearing on window solid analysis for this project. This is not done yet, it's just a rendering. This part goes, the structure is sitting on the rock, but the rock is dipping in and it's going to go to alluvium. About 110 feet is the length of the alluvium sulfide material. We have also the scalping problem. That's the bridge. Like I said, I'm doing the analysis now. We're doing the bridge on isolation bearing. And this isolation bearing is going to provide a fuse at the interface. We're going to have elastic super and substructure. It reduces the demand on shear and moment on the columns, reduces the load on the foundation, and therefore our foundation system and substructure will be completely elastic. Steve, I'm almost done. So I'm going to go through a calibration we did with Guyana. We have this grid instrument that we wrote in California. Through one by contact with Mars. Said, hey, maybe we should look at this bridge, see if Guyana is capable of doing this bridge. Here is the bridge. So basically the part about very massive, the bridge has instrumentation on the top, seismic instrumentation. These are the seismic instrumentation on the bridge. We developed a 3D model. These are existing piles, these are retrofit piles. So here is one of the models. We're just looking at the substructure, just one of the foundation. We shoot it with a recorded motion. So you see how foundation is moving. This is actually recorded motion from vertical to rear. So this is another detail of the foundation. We have existing piles or ladder edge piles, but then we have this rounded piles. And this is another shot of part of the model, which we're looking at piles, columns, and the superstructure. So you can see how it moves. So when you develop a model, you need to start testing as you go. You want to make sure your foundation works, then you want to show a column and a superstructure work, and then you put the global model together. Don't start from scratch for a large model, because if you don't make a mistake and you make a mistake, you cannot find it. Okay, so here is the full 3D model of Guyana. It has all the nonlinear foundation, nonlinear springs. This is one of the columns that we're looking at with the pile foundation. Input motion is here. We took the input motion and checked the superstructure, and we have recorded motion at various locations of the structure. We also, that was a beam spring model. We also developed a continuum model. The elastic part of it is done, but I think we're still looking at the nonlinear soil property and see how we can incorporate also the nonlinearity of the soil and everything in the model. On the beam spring model, this is the recorded motion. And then we're getting a response this is one of the stations on the bridge. Station on the top, these are recorded motion, and we're able to match the recorded motion versus the calculated motion. So this is the recorded motion, which we add our input, and the response of the bridge is using the one of the channels, recorded motion channel 10 is the red line, and calculated, and the blue is the recorded motion on the bridge. Very good. So here is the global model of the bridge. We build the model in pieces, and here's the global model. develop the one, took a lot of time. And I can stop where I can go. Okay, yes. I have stuff on the liquefaction lateral spread, how we do this with Diana, but I guess we will set up workshop in the future to talk about all this in detail. The workshop is probably going to be a couple of days, just show how we do calculation, how you design this. And also we have stuff on the liquefaction lateral spread, how you can use this Diana to do liquefaction lateral spread, how to calculate displacement, and when the stone pushes into the pile, how you form plastic hinges, and basically talk about serviceability of the pile. With this, I guess this is the end of it. If you have any questions after during the break, I'll be happy to answer. But hopefully in the future we set up a workshop that we can go through this in detail and show you how you do this actually from the model. Okay?
Thank you.